Hello everyone and welcome to the Reigning Grades Kingdom. My name is Elle and today is all about phase changes, like solids, liquids, gases, and maybe even some supercritical fluids in there. But before we get into the video, make sure you go downstairs and click that like button, and also don't forget to subscribe so you can be notified whenever I post new videos. So without further ado, let's make it boom. Like I mentioned before, phase changes is changing between a solid, liquid, gas, or supercritical fluid in any order, but for this video we will be mainly focusing on solids, liquids, and gases. Well, what's the difference between a solid, a liquid, or a gas? Really? Well, I'm glad you asked. You see, it all has to do with intermolecular forces. Solids have strong intermolecular forces, which is why the molecules are so tightly compact, and solids have a definite shape. On the contrary, gases do not have that luxury and are very free-moving and do not have a definite shape. And liquids are in the middle and take the shape of whatever container they're in. Now, whenever we move between these phases, we have to either add energy or subtract it. So let's take water for instance. It's kind of common knowledge that when water is below 0 degrees Celsius, it's solid. But if we add heat to it, it will start to melt at 0 degrees Celsius, the melting point. And if you keep adding heat to it, it will boil at the boiling point, which is 100 degrees Celsius. But if you start in the opposite direction with a gas that's greater than 100 degrees Celsius and you subtract energy from it, you'll get to the condensing point. And if you keep going, you'll get to the freezing point. So what does all this look like on a graph? Well, if we graph temperature as a function in respect to time, it'll look a little something like a stepping staircase. For this example, we'll use water and start graphing it at an arbitrary temperature like -50 degrees Celsius, and then add the other temperatures in that constitute for the melting point and the boiling point. Now let's take a look at what's happening at each of these sections. At section number 1, you're going from a solid to a liquid at the melting point. Then at section number 2, you're remaining at 0 degrees Celsius. Now, why is that? It's because at this point, not every single molecule has gone through the phase change, so you have to wait until everyone is caught up before moving on to step number 3, which is boiling at 100 degrees Celsius, and then staying here for the same reason until moving on to step number 5, when all of the molecules boil away into a vapor or a gas. Now, of course, all of these temperatures are correct for water, but only assuming that the pressure is 1 atmosphere. Now let's look at these changes on a graph that shows the effects of pressure and temperature on the phase changes. Phase diagrams are very helpful in showing the expected effects of high pressures and high temperatures, as well as low pressures and low temperatures on phase changes. It shows each of these changes as a curve on a graph, and whenever a pressure or temperature point lies on a curve, we say that the substance is in equilibrium according to whatever phase change is on either side. That means this triple point is extremely important then, because that is when it is in equilibrium as a solid, liquid, and gas. So now I'm going over the curves with different colors so I can redefine it a little more clearly. Now we'll start plotting points so we can see the relationship between pressure and temperature. As you can see, that one was in equilibrium between liquid and gas. And this next one is purely a gas. So then if we keep the same temperature and go with a higher pressure, we get a liquid. Whereas if we go with a super high pressure and a super high temperature, we'll get a supercritical fluid. And if we keep a moderate pressure with a low temperature, we'll get a solid. And let's not forget about the triple point. So while this was a phase change diagram, was it for water or is water different? Well, the answer is yes, water is different, and here is why. Not only does water have hydrogen bonding and a whole bunch of cool other attributes, but as you can see on this phase diagram, the line separating the solid from the liquid leads slightly to the left, meaning that it becomes a liquid at higher pressures and lower temperatures. But how do we know that? How could we test it? Well, actually it's pretty simple to test, and you could do it right now. All you'll need are 2 ice cubes and a mouth with teeth. So what you do is place both ice cubes in your mouth and apply gentle pressure with your teeth. Then once you release the pressure, it should be as one, because under the high pressure it turned into a liquid, and when you release the pressure, then it turned into a solid again and fused together. All of this is great and all, but how does it all apply to real life? What if I was cooking in a place with approximately 1 atmosphere of pressure and used the same recipe in a place with a lot less pressure? Well, because of that last phase diagram we saw, we know that lower pressure equals a lower boiling point for water. Again, as you can see, that slight shift in equilibrium between solid and liquid makes the boiling point go down as the pressure goes down. So your recipes in South Philadelphia will not be the same in Denver, Colorado. Sorry, Mildred. Thank you so much for watching this video. I hope that I helped you get an A on your test. Much love always from Al, and I'll see you again soon in the kingdom.